Hi everyone, and welcome to this video covering some of the review questions that were asked about in our Unit 1 Kinematics unit. The first question says, what is the x component of the displacement vector delta d total equals 36.0 meters south 38 degrees east? What is the x component? So what we're looking for, and we should have a vector on that, what we're looking for is the part that's in the x. What is that? Because there's a portion that's in the x and a portion that's in the y. So if we actually draw this vector, keep in mind that northeast, southwest, that should be pretty familiar to us. South 38 degrees east is going to have a 38 degree angle in here. So we actually draw this vector, it's going to look something like this. South 38 degrees east, and my total displacement in the y is this vector, and my displacement in the x is this vector. And so I've gone from here, ended here, and we can think about it in terms of the x part and the y part. And so you'll notice here that the x, compared to the angle, the x side is the opposite side. The y side is the adjacent side. And so in this case, we know that delta dx, because it's the opposite side, the only one of sine and cosine that has opposite is sine. So it's delta d total times sine of the angle. Now keep in mind we can let this have a positive direction. I'm going to let it be positive is down, and or south, and east is also positive. Okay? So with that in mind, we can let this be a positive value, knowing that that means it's going to be down or south. And so we go 36.0 meters times sine of 38 degrees. And we get a final answer of 22.1638 meters. We're keeping a few significant digits. However, this answer is 2 sig dig, so we would say it's 22 meters. And we could also say it's south, or we could say, based on our diagram, we could say it's 22 meters south. So that's the final answer. There's a couple of mistakes that people make. And the first one is they assume that anytime we have an angle from a vertical like this, that the opposite side is the y, and that's not the case here, as you can see from the diagram. The other mistake people make is they just mix up sine and cosine. And the final mistake that I see people make is they don't have their calculators in degrees. So make sure your calculator is in degrees. Okay, let's look at the next question, number 9. Number 9 says, 4 students traveling to a sporting event make a mistake with their directions and end up traveling out of their way. They are able to use a map to get themselves back on track, but their mistake caused them to travel 15 meters north and then 5.3 kilometers west. What displacement resulted from their wrong directions? Well, again, we've got the north, south, east, west, and we know that if we're going north, we're going 15 kilometers north. So here's your first displacement, and then you're going 5.3 kilometers to the west. So you're going on this direction. That's your second displacement, is 5.3 kilometers. This is 15 kilometers. So our total displacement is going from where we started to where we ended. All right? And so that's the total displacement that we're trying to find. Well, we know that the total displacement is equal to delta d1 plus delta d2. And some would say, well, can't I just put those numbers in and get an answer? Well, clearly not. We know it's a right triangle. So this means, again, this means this picture, but what it actually means in terms of the mathematics is we're going to say delta d total squared is delta d1 squared plus delta d2 squared. It's the Pythagorean theorem. And so we go delta d1 is 15 kilometers squared. Delta d2 is 5.3 kilometers squared. And that gives us a total of square root of 253.09 kilometers squared. Now you notice I didn't put this in SI units, right? It's still in kilometers, and that doesn't matter because we're just dealing with only kilometers here. But if we were dealing with one of the equations of motion, for example, we would need meters and seconds, not kilometers. And here this gives me, when I take this is delta d total. So up before it's delta d total squared. So when I take the total displacement, I get 15.91 kilometers, which we should check this because it's a right triangle. The hypotenuse should be longer than the other sides, and in fact it is. But we're not done yet. We've just found the length of that. Now we need to find the angle. And so whenever we're given two sides that aren't the hypotenuse, we could use any trig ratio technically. But it's better to use the numbers that we were given than the number we just calculated. So we're going to use tan because I know the opposite side and I know the adjacent side. And tan theta is opposite over adjacent. So now we take tan inverse to get the angle. And the opposite side is delta D2. And the adjacent side is delta D1. And so we take tan inverse of those two numbers, which is 5.3 over 15. And we get a final answer of 19.46 degrees. So we can conclude, therefore, the total displacement is 2 sig digs, so it's 16 kilometers, and it is going to be, according to the diagram, it is north, and then it's 19 degrees, 2 sig digs, west in this case. So that's our total displacement for this question. Let's have a look now at number 11. Number 11 asks a history question, which if you've been reading the section you would know, but I haven't explicitly pointed this out in class. It says, before Galileo performed his experiments with falling bodies, which one of Aristotle's theories was considered to be true? A. All objects fall at the same constant rate no matter what their size. Objects fall at a constant rate with heavier objects falling more quickly than lighter objects. C. All objects accelerate at the same rate when falling. Or D. Smaller objects fall more quickly than larger objects. So before Galileo, people thought that the answer correct answer there is B. They thought that objects fall at a constant rate. However, heavier objects fall faster. That is not the case now. What we know now is that was what we thought before Galileo. Now, what we know to be true is C, that all objects accelerate at the same rate when falling. Now hold up a second, you say, but what about air resistance? So we can add that little bit to it. They all fall at the same rate when falling if no air resistance. And so if there's no air resistance, we call this being in a vacuum. Not that we're in a physical Hoover vacuum, but that we're actually in a place where there's no air. And so that's a nice lead into our next question, which is number 22, and we're going to talk about how this works. And I'm then going to just mention a video, and I'm going to put it in the link below this video. That's really cool. They actually dropped a feather, a bunch of feathers, and a bowling ball in a vacuum. And I encourage you to check it out. So number 22 says this: if a bowling ball and a feather are dropped at the same time from the same height in a vacuum, then the bowling ball will hit the ground first. Well, in our experience in everyday life, we know that's not the case. We know in everyday life, if you drop a feather, here's my feather, terribly drawn, I know, but here's my feather, and here's my bowling ball, we clearly know that there's going to be more air resistance pushing up against this that's going to affect it greater, and this one's going to hit the ground first. But if there's no air resistance, they will hit at the same time. Don't believe me? Check out the video I'm going to post below. The last example we're going to go over here is I'm going to walk through again an example on how to find the algebraic solution to two different vectors added together. So let's do that. So I'm just going to revisit the example we looked at earlier in this unit, and hopefully as we go through it a second time, maybe with a bit of a different explanation, it'll help click if it's not yet. So let's consider the question of Jill traveling in a boat east 40 degrees north for 900 meters, then traveling south for 700 meters. The question asks, what is Jill's displacement? And so I encourage you at that point to also switch up the order in which you're adding the vectors. And so let's see what that looked like. Now I don't have the scale necessarily that you would have on your paper, but it's going to look something like this. A scale of 1 centimeter to 100 meters, meaning that this right here is 9 centimeters, this here is 7 centimeters, and likewise if you drew them the other order, that's 7 centimeters and 9 centimeters. What's the point? The point is that because if you added the first vector and the second vector in that order, you get a total displacement that's the red vector. Likewise, if you added the second vector plus the first vector, that total displacement vector is exactly the same direction and should be exactly the same length as if you'd done them in the other order. So the order of adding vector parts doesn't matter. And that's the basis of why we can break these up into components. Because if I break this first vector, delta d1, up into delta d1x and delta d1y, then what I'm doing is I'm adding delta d1x plus delta d1y. That gets me to the end of delta d1. That gets me there. And then I'm going to add delta d2 to that, which gets me back down to here. So the order of those three vectors still makes me arrive at the same final destination, giving me the same total displacement. So I'm actually going to break this delta d1 into its x and its y components. And then what you can see is when we add the y components together, the y of the first vector plus the y of the second vector is all y, that's going to give me a total displacement in the y that's represented by this. And then the total displacement in the x is represented by delta d1 in the x. And so this represents the total displacement in the x. And what I'm left with now is I'm left with this right angled triangle. So if I add the y's together first in the first step, and then I consider the x and then adding to the difference in the y, that's going to give me that right triangle, allowing me to find the total displacement. So let's look at how to do that. So the first thing I want to do is I want to break delta d1 into its two components. So the first thing is break the first displacement into two components. We don't need to break the second one because it's already only in the y component. If it was also at an angle, we would have to break that one up as well. So what we're going to do is we're going to say delta d1x and delta d1y. Well, just like we did a minute ago when we broke a vector into components in the first question we took up, we're going to look at this and say, well, this is the triangle I'm solving right here. And let me go around over this again with it just to show that, make it nice and clear. Delta d1x is the adjacent side to the angle. Delta d1y is the opposite side to the angle. If it's the adjacent side and we know the hypotenuse, that's going to be cosine. So it's delta d1 cosine of the angle. If it's in delta d1y case, it's the opposite side, hypotenuse and opposite, that's going to be sine. So it's delta d1 times sine of the angle. Now some of you are like, well, how did you just jump to that? Well, what I did is we've done this step before, but we know that cosine of the angle is equal to the adjacent delta d1x over delta d1. And so we're just rearranging that. We're multiplying both sides by delta d1. It comes up onto the side with the cosine, and we're left with delta d1x by itself on this side. Now if I'm going to specify a positive direction, then I'm going to say that down is positive, or south is positive, and I would probably say that east is positive as well, because overall that's going to give me positive lengths. It doesn't matter, you just get a negative if you have a negative length. Or if you said up north was positive, then this value for total in the y would be a negative value. But then when you square it in the Pythagorean theorem, it's not going to matter. It's going to get rid of the negative. So there we have it. We have delta d1x, we have delta d1 in the y. And so we can go ahead and calculate that, and we did that together already. And you can see there that we sub that in. Delta d1 in the y was 900 meters times sine of 40 degrees. Actually, we swapped that here. So there's the y, there's the x. So delta d1 in the y is 900 times sine, and delta d1 in the x is 900 times cosine. And then we solve those, and we should look at that, and we should be able to say, well, does it make sense that the x component is bigger than the y component? Look back at the diagram. Should this be bigger than this? Absolutely, because that angle is only 40 degrees. If that angle was bigger than 45 degrees, we would expect the y to be bigger. And so that's just a mental check to make sure we're on the right track. So now what we do is we add the y components. We already know that the total in the x component is the displacement in the y in the first vector, in the x. And then vertically, we had the total displacement, or the displacement in the y. That was the part that was up, followed by the displacement in the y. That was the part that was down in the second vector. The second vector was completely in the y direction. And so we're going to get, by adding these two together, we're going to get a displacement vector, total displacement, that is just this little segment right there. And so you'll notice that delta d1 in the y, if you're saying south is positive, then that needs to be a negative value. And then delta d2 in the y is going to be a positive value. And so making sure that we're only adding those if we've considered that they're both in the same direction. So this is negative, the other one's positive. And so this should make sense to us because we get a total displacement in the y that is a small number relatively. So let's look back at the diagram and see what this means. We got 121 and 689. What this means is that this total displacement in the y is 129, and this total displacement in the x is 689 kilometers. Okay, point something kilometers. So now we're just solving this right triangle down here on the bottom. And so we know the adjacent side, we know the opposite side, we need to find the angle, and we need to find the length of delta d total. And we've already done that in this video, but I'll go over that again quickly here. So what we're doing now with that triangle, this is the total displacement in the x there on the top, total displacement in the y. And what we're going to do now is we're going to go ahead and we're going to solve for the hypotenuse. And we're going to use the Pythagorean theorem to do that. And I know you know how to use the Pythagorean theorem, so I'm not going to bore you with the details on that. And then we're going to find the angle. And the angle is, because we know this is the adjacent side and this is the opposite side, I have to use tangent. And tangent is opposite over adjacent, or delta d total y over delta d total x. And then we can just sub those in. The units are going to cancel out, so you don't need to worry about those. And so to get theta by itself, we take the tan inverse, and we get an angle of about 10 degrees. Now, you can just ignore there what I've written at the bottom. But this angle of 10 degrees, we can write it out to two significant digits, and we can say its Jill's displacement is 700, so 7.0 times 10 to the 2 meters, east 10 degrees, and I'll put the decimal place after the 10 so it shows 2 sig digs, south. And so what you should do at that point is you can compare that to your scale vector diagram and see if your answer was any more accurate this way than it was with the scale vector diagram. Now, you might have gotten the exact same answer here, and you might conclude, well, the scale vector diagram then is just as good. Why do I even need to do the math? And I would say, well, these numbers worked out really nicely. Nice whole numbers. However, you'll find that the numbers don't always work out very nicely, and you're going to get a slightly more accurate answer using the algebra. So just reflect on that, think about that, say, hey, does that make sense? 700 meters. Let's go back and just look at the diagram. 700 meters, yeah, it's about the same size as this line going south. And 10 degrees, yeah, that angle looks about 10 degrees. So that answer seems to make sense. So I hope that's helpful. All the best as you study and you review for our test.